In the first part of our discussion in this section, we talked about ways to declare different data types and allocate memory in x86 architecture using our Microsoft Macro Assembler. So these are some examples that we've used. And in the second part of our discussion this week, we're going to look at CPU flags and data manipulation. So we begin by looking at some of the arithmetic instructions. So as we try our examples, I'm just going to rename the title of this program to CPU flags and data manipulation. And let's just clear up our data segment and also start new examples in our main program. So these are a few examples of adding and subtracting integers. Mainly we're going to focus on integer arithmetics this semester, and later on we're also going to switch over and look at some of the floating point arithmetics. So right now the possibility of addition and subtraction with integers can be done with addition, increment, subtraction, and decrement instructions. So if there are two operands, only one operand can be in memory. So let's take an example of these three instructions. I'm just going to copy and paste them into our main program right here. So obviously addition instruction just basically takes two registers and adds them together, so the result is stored on the left hand side. So EBX plus EAX. So in other words, we can just write this as a pseudocode like this. So EBX equals EBX plus EAX. In most of the high-level programming languages, you probably just write it like this, right? So you just say EBX plus equals EAX. So that's the idea. When we add EAX with something specified by register EBX, it means that the register is pointing to a double word in memory. So let's go back to our data segment and create some sort of value here, and declare this double word and store 0 to begin with, right? So if we want EBX to be loaded with the location of our value, we can basically move into EBX offset of this value, right? So value is a label. So now we have an address that's pointing to this double word in memory, namely 0, and we're going to add. So let's just set this to something more or less predictable. Let's set it to 5, okay? And then we can also set EAX equals 0 by doing exclusive OR of EAX with itself. This is a pretty popular way to set a register equal to 0, because remember that exclusive OR instruction will set every bit. It's a bit by bit instruction, bitwise instruction that looks at differences between the bits. Of course, there is no difference between EAX and EAX, so as a result every bit of EAX will be reset to 0. Essentially, this is the fastest way, in fact the fastest and the most efficient way to set register to 0. So when you see something like exclusive OR of something with itself, it means this, just assigning 0 to this register in our case. So now EAX is at 0, EBX is the address of this memory location right here containing 5, and we're going to take 0 plus 5, right? So this would be, if we want to write as a pseudocode for something like this, we can say EAX plus equals, you know, whatever EBX is pointing to. So this will be essentially plus value, right? Plus value. If value was a variable, then we could say plus equals like this. Also, we can add to the value directly, because the value, of course, translates to the offset of this integer in our global data segment, and we can just add this as hexadecimal 10, right? So we can add immediate value 10 to a double word. So let's see if this can be assembled properly. Right, so what we do is just do, I'll try clean a solution first, and then make sure that we have configuration set to x86, and now we can build in this configuration, and see it comes out pretty nicely. I just continue to use the same project that we started earlier in this section. So it just runs, and of course we can try stepping through this in debug. So if I start debugging, or just press F5 like this, the application starts, and it runs through the entire application. Of course, we don't interact with the user, so one option that we can try is debug and say a step into, or set a breakpoint somewhere here. But let's try to step into. So stepping into brings us over to the first instruction that belongs to our application code, which is this addition right here. So I'll close some of my debugging windows here, because I really don't need them, except I will go to debug windows and open registers window, because registers is like immediate access to our registers. So initially EX and EBX contain some memory addresses that we just ended up having in these registers. That's fine. We're just going to add them together, which makes no sense, but it's just a demonstration of arithmetics. I press F10 to step over this instruction. You see that EBX got this value that is now the sum of EBX and EX. As I step over to the next line, you can see that EBX now is loaded with the address of our integer 5 in computer memory. Now look how EAX is just about to be set equal to 0. We step again, making another step. So EAX is now a result of exclusive OR with itself, which is always 0. And now we're going to add EX and the address that we're pointing to in memory, which is this value. So of course the result of this is that EX got updated to 5, which is equal this. And now we're going to update value of 5 with hexadecimal 10. Okay, so we're going to do this one more step, and of course we just stepped over. If we want to find out what is the new value of this integer in memory, of course we can go to debug windows, open one of the memory windows like this, and since the address of value has been already loaded into register EBX, we can just take this address from already prepared in EBX and paste it in here, hit enter, and you see that this is hexadecimal 15, which is the result of hexadecimal 10 plus 5. Okay, so that just totally makes sense that our register got, our memory was of course updated by this addition instruction. So this is the idea that if we have two operands, right? So we have two operands, only one operand can be in memory. So when we use square brackets, that indicates that our operand is in memory, and this time a register indicates a location in memory. This time is just a hard-coded label which knows its offset in data segments. So that's the second way to access the same register in memory. So these are demonstrations of adding and subtracting integers, and these are the formats of instructions that we demonstrate these two possibilities.